So in the next 1 hour and 30 minutes, you can expect first an introduction to VyPR, which is a framework for performance analysis of Python programs, and then an in-depth description of the past 3 years of contributions to both the runtime verification and software engineering communities made by VyPR and its underlying theory. Finally, we will give a live demonstration of VyPR being used to analyze the performance of a real-world system used at the CMS experiment at CERN. All of the materials for this tutorial can be found at various links. For example, the VyPR project website can be found on a GitHub IO page. The tutorial materials can be found in a directory on the project website. And finally, the source code of all of the components is released on GitHub under the GPL v3 license. So we'll begin by thinking about the problem of gaining insight into the performance of a program. This typically involves the use of a profiler. So in this case, we focus on Python, for which we could use the cprofiler tool. In this example you see taken from the documentation, we import the cprofile library, we instantiate something from it, and then we use these enable and disable methods. And these enable tracing, which is a facility provided by the Python interpreter. And this would generate fairly detailed output of function calls, their frequency, and the time they took, which would be very useful. While profilers are very easy to use and the Python interpreter makes it very easy to implement one with all the facilities that it provides, the large amounts of data generated when analyzing performance data with respect to varying inputs can be difficult to analyze. There are tools to help us do this, but it's still tricky. Further, profilers measure single types of quantities, for example, just function calls, and these are also measured as independent quantities with no relationship to each other. Further, checking of constraints is possible offline, but checking constraints over combinations of quantities with no real relationship to each other becomes quite difficult. Now, what about explaining performance deviations? Explanation with information collected by profilers is restricted by the quantities that they measure, and most profilers focus on function calls, so explanation normally looks like, when the call tree looks like this, then we have a problem. Further, low-level behavior of programs, for example the code inside functions, is out of reach, at least in the Python setting, because tracing is required, and in this case, the amount of overhead that is generated would completely distort the performance being measured. So in general, the ability to explain performance deviations using profilers is quite limited. Our effort to remedy this situation takes the form of the VyPR framework, which enables software engineers to write source code level specifications about how their Python program should behave. With minimal modification of the source code by a software engineer, VyPR performs instrumentation before runtime, monitors for agreement with the specification during runtime, and then stores verdict data ready for it to be analyzed by software engineers offline using our sophisticated analysis tools. The VyPR framework offers several advantages. For example, conservative instrumentation based on specifications means overhead is usually quite low. A combination of the code required to be added to the codebase to activate VyPR and the conservative instrumentation means that the intrusion into the monitor system is minimal. And finally, formal specifications written in a low-level and rich language allow, firstly, automatic checking of constraints over multiple quantities measured at runtime, and secondly, multiple types of explanation to be offered whenever a given specification is violated. Now, in order to describe the VyPR framework, we will present the past 3 years of work that has made contributions to both runtime verification and software engineering. These contributions include our specification language, which includes the syntax and semantics as usual, a conservative instrumentation approach, and with this we will give worked examples and visualization, an efficient monitoring algorithm with which we will also give a visualization, machinery for explanation of whenever a specification is not satisfied by a program run, and finally sophisticated offline analysis tools that take the form of a web-based application and a Python-based analysis library. To conclude, we will show how all of the material presented has helped us to analyze the performance of a real system running at the CMS experiment at CERN. So let's take a look at our specification language contribution, which is specifically aimed for software engineers to use in the software engineering process. In particular, we designed a low-level temporal logic with the aim of providing a tool that can be used by the average software developer writing Python code. The result of this process was control flow temporal logic, or CFTL, and this was introduced in the SAC SVT conference. The distinguishing characteristics of this specification language include the fact that no instrumentation mapping is required, meaning that if we take an arbitrary formula written in CFTL, the meaning of that formula with respect to the program that it's been written over is immediate, Further, no knowledge of the usual modal operators such as next, until, or always is required, and this makes writing these specifications a little bit more straightforward for software engineers. And finally, the combination of the previous two, that is no instrumentation mapping and no knowledge required of the usual modal operators, means that a software engineer needs only to think about the source code that's actually being monitored rather than thinking about the mathematical background of their specification formalism. And this makes the specification process more straightforward. A CFTL formula expresses a property that should be held by a single execution of a function. This means that when we come to write a specification of how a system as a whole should behave, we do so by writing a set of specifications over each function in that system. So in order to write a single CFTL formula, we need to know the general form that we should follow. Each formula consists of universal quantifiers to capture events that happen at runtime. We'll develop a precise definition of events later. And then we have a constraint to check at each of these captured events. This structure of formulas allows us to first identify where in a program's runtime we'd like to check something, and then precisely define the constraint that we'd like to check as a mixture of various constraints that are allowed by the syntax and semantics of CFTL. Our first step in developing CFTL formally involves developing a model of functions, that is, a static model that we can build. So we start with a representation of the source code of a function called a symbolic control flow graph, and you see an example on the left. The SCFG of a function is a directed graph encoding potential changes of program variables or functions and reachability and control flow. For example, on the left you see that one of the vertices near the top we have a loop with the variable I being changed, and then we encode the loop structure as a cycle in the graph. We're going to see plenty more examples of symbolic control flow graphs derived from real programs over the course of this tutorial. Here we see an example of a symbolic control flow graph on the right, with its corresponding program on the left. So you see that constructs such as for loops, as we have here in the program on the left, are encoded by vertices and then cycles, as I mentioned before, but we also have this notion of a symbolic state, which encodes the potential change of a variable or the potential call of a function. For example, we have b equals 10, and this corresponds to the vertex b in the symbolic control flow graph. But notice that there's no information about concrete values stored in this because it's only a statically computable structure. Similarly for the function call that you see highlighted below. So in this case we have a change of the variable result2, but then we also have a call of the function calculate something. So in this case we're not encoding anything about the concrete values that might be obtained. Rather, we're encoding information about the possibility of certain things happening, like variable changes or function calls. Finally, the edges in a symbolic control flow graph also have meaning. For example, instructions in the code that are consecutive also have edges between them in the symbolic control flow graph. And this leads to the fact that edges model the potential computation that would happen to get from one state to the next. We now need a model of function executions because it's over these structures that we will actually define the notion of truth of our specifications. For control flow temporal logic, we represent an execution of a function by a dynamic run, which we denote by D here. A dynamic run can be described as a sequence of checkpoints reached by a program at runtime. To look more closely at a dynamic run, here we see highlighted in blue an example of a concrete state. Now this is a triple whose first element is a symbolic state from a symbolic control flow graph, whose second element is, we say, a concrete mapping from variables in the program to concrete values that they obtain, and the third element is a timestamp. So you see, if you look at the multiple concrete states that are in this dynamic run, the timestamps are monotonically increasing, as you would expect from something generated by the runtime of a program. Intuitively, concrete states are instantaneous checkpoints that a function execution must attain. We can then pair these concrete states to make transitions, and these transitions model the computation that occurs to move the function execution from one concrete state to another. We normally denote these transitions by using this arrow-like syntax. So on the left you see we have a normal concrete state, and on the right we have a separate concrete state. So normally the two concrete states in a transition will be consecutive. Now the fact that concrete states are related to symbolic states has the consequence that a dynamic run, being a sequence of concrete states, can be related to a path through a symbolic control flow graph. This means that our representation of a run of a program, the dynamic run, can essentially be seen as a path through a symbolic control flow graph, which is ultimately our representation of a program. With symbolic control flow graphs and dynamic runs introduced, we're in a position to talk about the semantics of control flow temporal logic. The CFTL semantics is built on dynamic runs, not surprisingly, and here we see that if we take a CFTL formula with the normal form that we introduced before, we have the quantifiers on the left and then the innermost quantifier-free part on the right, then we can begin to say what exactly these things actually mean that are in the formula. For example, before we said that on the left the quantifiers capture certain events that happen at runtime, and now we can say precisely that these quantifiers capture sets of concrete states or pairs of concrete states, which we call transitions. Further, we can introduce the notion of a predicate and say that a predicate is a rule that defines which concrete states or transitions should be used when evaluating the CFTL formula. And finally, we can now say that the innermost quantifier-free part of the formula should be evaluated at each one of these concrete states or transitions identified by the predicate gamma and bound to the variable q. Now, to go into more detail on the subject of predicates, the CFTL semantics includes multiple predicates that can be used to capture either sets of concrete states or sets of transitions. Here we see two examples. So in the first one, we use the predicate changes and then a variable x. So x here is a program variable, and we want to capture every single concrete state in which x has been changed. Now we say formally that a concrete state changes a variable, in this case x, if the symbolic state with which it's associated indicated a potential change of x. And using this definition, the predicate changes x would capture all such concrete states and bind each one individually to the variable q, so that can be used in the innermost quantify-free part of the formula. We now pass on to the next predicate, which is calls calculate something. So this is a similar idea to the previous predicate, except in this case we capture transitions. And again, we use the symbolic control flow graph information that's encoded in the concrete states. For example, in this case we have a transition, which is a pair of two concrete states, and then we say that a transition satisfies this predicate if the second concrete state in that transition points to a symbolic state which indicates a potential call of the function calculate something. Here we see an example of these two predicates being applied to an actual dynamic run. So in this dynamic run we have a number of concrete states, and then we have a transition between each one of these concrete states. You see the top left we have the predicate changes x, and we suppose that this identifies a state, and then the top right we have the predicate calls of calculate something, which identifies a transition between two concrete states. We can go further with predicates and define more complex ones by combining multiple. To help with this, CFTL introduces the future predicate. So you see here that we have first a predicate changes x, and this binds appropriate concrete states to the variable q. But then we say that, okay, given this variable q, whichever concrete state it's holding at a specific time, we want to look in the future of that concrete state and find all of the calls of the function calculate something. The result of applying these two quantifiers to a formula in CFTL is that the innermost quantify-free part of the formula will be evaluated using pairs. In this case, the pairs will consist of concrete states, captured by the first quantifier, and then transitions, captured by the second quantifier. An important detail to take note of in this case is that if there are multiple future calls of the function calculate something after a single change of x, then multiple pairs will be generated with the same change of x, but a different call of calculate something in the future. We see this idea illustrated here. For example, if we suppose that state 1 is identified by the predicate changes x and therefore given to the variable q, and then suppose that first of all the transition between state 2 and 3 satisfies the predicate calls of calculate something, but then also the transition between state 3 and 4 satisfies the predicate calls of calculate something, then we have this repetition. In particular, we have two pairs consisting of a left and a right-hand element for q and c, and in each of these two pairs, q is given the same value. And this is because we have supposed that there are multiple calls of calculate something in the future of state 1. Therefore, these will be identified by the future predicate. Now, once we've defined our quantifiers and thought about which parts of the program run that we want to select and apply constraints at, we need a way to write the innermost quantifier-free part of our formula. Now, the syntax provided by CFTL for this is extensive, and we won't describe it all because it would take a few slides. Instead, I'll give some examples. So in this first example, we consider the property that for every transition that satisfies this predicate, so every transition that is a call of the function calculate something, then we want to check whether its duration was less than 1 unit of time. So you see that we use a quantifier with the variable t and the predicate calls of calculate something. So each transition that satisfies this predicate will be given to the variable t, and then for each value of the variable t that we derive via this predicate, we use the duration operator, which is defined by CFTL, to take the difference in the timestamps between the two concrete states used in the transition. Once we've measured the duration, CFTL then makes it easy for us to compare this to a numerical value. We can then easily write more complex constraints. For example, in this case we have one quantifier, but then the innermost quantifier free part of the formula takes advantage of the standard Boolean connectives that CFTL supports. For example, in this case we say that for potential changes of x, if x is greater than 10, so on the left-hand side of the implication, then the next call to the function calculate something should take less than 1 unit of time. As you see on the right-hand side of the implication, we have the duration operator, but then inside the duration operator we introduce a new feature of CFTL, which is the next operator. And this takes a concrete state or a transition, so in this case the concrete state held by the variable q, and then searches forward in time for the next concrete state or transition that satisfies the predicate given. We can also define more complex specifications using multiple quantifiers like we saw before. For example, in this case, we first use the predicate changes and bind every concrete state that this identifies to the variable q. We then use the future predicate along with calls of calculate something to bind future transitions that satisfy the calls predicate to the variable t. But then we introduce a new operator which is time between. And the idea here is that we can give this operator two states and then reason about the time between these two states. So you see that we can give it directly the variable q because this already holds a concrete state, but in the case of t, this holds a transition. So first we have to use the dest operator to obtain the second concrete state in the transition. And once we've done this, we can compare the time between these two states to a numerical value.